Okay, here's problem 3 from the 8.9 part 2 worksheet. Okay. All right, so first I'm just going to write. All right, so the initial case, so that never works. The initial case is that lambda is an S. Recursive rules. If xy is an S, then we have 3 recursive rules. We got recursive rule 1, AXB is an S. Recursive rule 2, BXA is an S. Recursive rule 3, XY is an S. Okay. Right, remember so the property we're trying to prove, let's see, maybe I should use a P of X. X has the same number of A's and B's. Okay, so base case. Here we're trying to prove the property holds for the initial case. So we're trying to prove P of lambda. So P of lambda, that says that lambda has the same number of A's and B's. Okay. All right, so the proof here is basically like, I mean, lambda is the empty string. It doesn't have anything, right? So it has nothing in it. So it has 0 A's and 0 B's, right? 0 is the same number. So lambda has 0 A's and 0 B's. So P of lambda is true. Okay, so now we're going to deal with each of the recursive rules. All right, let me write that as inductive step. The inductive step, we assume that this is true for x. In this case, x and y because of recursive rule 3. Okay, so we're going to assume P of x and P of y. All right, so we're assuming that x and y are elements of S. They're strings in this set S. We're assuming that x has the same number of A's and B's and that y has the same number of A's and B's. Okay, and we're going to say, okay, let's say that z is a some string in S created by recursive rule 1. Okay, so z equals AXB. Okay. All right, so we're not trying to, one thing I should emphasize is that we're not trying to prove that Z is in S. Z is already in S. We already know that's true. So proving that Z is in S doesn't make any sense. That's already true. We already know that's true. That's true by our definition here. All right, but all we're trying to prove is that for the z that is in S, that's true. That z has the same number of a's and b's. So what do we want to show? To show p of z. All right. We want to show that z has the same number of a's and b's. All right, and we already get to assume that x has the same number of a's and b's. Okay, so z has one more a than x, and z has one more b than x. Since the number of a's in x is equal to the number of b's in x, number of a's in z is equal to number of a's in x plus 1 number of b's in x plus 1, which equals number of b's in z. All right. Now notice that where we use the induction, notice where we used the assumption that x has the same number of a's as b's. Right. That's right here. Right. X has the same number of a's as b's, right? So if you if you add one more a and one more b, if you add the same number of a's and the same number of b's to z, then you're still going to have the same number of a's in b as the same number and the same number of b's in z. Right? Okay. All right. So notice this is almost entirely similar as recursive rule 2. Pretty much everything will be exactly the same. Recursive rule 2, just put a little 2 there, a b there, and an a there. Z still has one more a than x, and z still has one more b than x. So the number of a's in x is still n is the number of b's in x. This is because of our assumption p of x. So that shows what we need to show there. Okay. All right, recursive rule 3. Z equals xy. Again, we want to show p of z. We want to show that z contains the same number of a's and as b's. Okay. All right, so let me just think about how I would do this now. All right. So again, yeah, it seems pretty clear, right? But we're going to work it out. Let's see. So I still want to use the same idea. The number of a's in x is equal to the number of b's in x. All right, let's say since we assume p of x and p of y the number of a's in X is equal to the number of B's in X and the number of A's in Y is equal to the number of B's in Y. Right, that's the inductive assumption, basically, is that the number of A's in X is the number of B's in X, and the number of A's in Y is the number of B's in Y. That guy's moving. Okay, so number of the number of A's in Z. Right, so the number of A's in Z, this is the number of A's in X plus number of A's in Y. Now because both of those are equal, right, that's equal to the number of B's in X plus the number of B's in Y, which is equal to the number of B's in Z. Right, so that proves that the property P holds for Z for recursive rule 3. So that's our proof.